In the last few videos, we've talked about methods of figuring out where a max and a min is analytically. But the reality is there are a lot of situations that you might encounter where finding that max or min analytically is very, very difficult. So for example, let's imagine that you're dealing with some situation where the function that your objective function is the solution to a differential equation, or involves solving a differential equation for each point that you're interested in parameter space, right? And you'll remember one sort of simple example of this from back in the days of ModSim. You might remember the great Manny Ramirez problem, right? Where you were sort of trying to figure out, what angle and what velocity to shoot a baseball at in order to make sure that it crossed over a fence, so that it got a certain distance, and you wanted to sort of do that while minimizing what the amount of energy was that you put in, right? So this is a case where this distance that the ball travels is a solution to involve solving a two-dimensional differential equation that doesn't admit to analytical solutions, so it's going to be a nasty problem to have to evaluate at every point in space,
sure,
right? So for that reason, it's often the case that you want to be able to find maxes and mins without actually evaluating the function everywhere. It's computationally expensive to evaluate the function everywhere. And so in this video, we're going to talk about ways to find maxes and mins without evaluating the function. Now, this is covered in Giordano, and we just want to sort of illustrate a couple of ideas in these videos that maybe are not as clear as they could be in Giordano, particularly to connect with some of the things we've been talking about in class. So in this video, we're going to talk about methods of gradient descent. And I want to emphasize that we're not really getting into, at this point, what the sort of best methods are here, so much as just ways to think about this and ways you could implement computationally. There are certainly more efficient ways of doing this. We just want to introduce the ideas right now, and then we can certainly point you in the direction of resources for really doing it efficiently. Okay, so the sort of core idea of gradient descent is one that you've actually already sort of dealt with. Because if you remember on, for example, the Florida problem, right?
Oh, the one that the Chicago.
Right. So you go. The Chicago problem, not the Florida problem. But the heat seeker, right? This person's standing in Chicago and tries to decide which direction they ought to walk. And rather than just simply going to the airport and saying, I'd like a plane ticket to somewhere warm, they instead decide to follow a gradient descent method, where at each point they ask, what's the direction I could move that would get me hottest, fastest?
And they ended up in Florida.
And they end up in Florida, which is not a bad solution. On the other hand, it probably took them longer to get there than it might have had they bought a plane ticket. So the core idea of gradient descent is sort of a follow your nose idea, which is to say that at each point when you ask the question, what direction should I move, the answer to that question is you should move in the direction that's going to result in the fastest change.
So would that be the gradient?
That would be the gradient.
Huh.
Okay. Now, there are a couple of different methods for doing this. One way of doing this is to move in the direction of fastest change just for some distance, and then to reevaluate where you are, and then take another step, reevaluate where you are. So one method, and this is the method that Giordano talks about, is one where you basically sort of step and keep on stepping until you're good enough. But you take steps that are sort of nominally constant size or increasing size, and you just keep on doing that until you're happy enough, right?
Mm-hmm.
Another method that's actually more commonly used is one that involves actually moving in the direction of the gradient until it's not worth anything more to move in that direction, and then recomputing your direction. So another option is sort of move along the sort of gradient tangent line until no more benefit.
Are you going to tell us how you can tell there's no more benefit?
Yeah, and I just want to outline, these two examples, and why don't we do an example of both of these?
Sure.
And sort of see how they work out, and also how they fail, because both have problems. All All right, so I first want to start with just showing you the function that we're going to use. This is a very popular function from MATLAB called peaks. It's nice because it has peaks, so it's sort of handy. I show you the function this way first so that when we look at a contour of it, you sort of know what you're seeing. You'll notice there is a peak right here. There's another peak here. There's a little valley that's located in here. There's obviously a deep valley here, a deep valley here, and there's another peak there, right? And this is a contour plot of that peaks function. So as you can see, there's the big peak there, there's the little peak, there's that little valley, there's the sort of medium-sized peak, the medium valley, and the deep valley, right? Okay, so let's first just think about what Giordano's method would look like on this. So where should we start? What would be a good point to start at?
Before we start, are we trying to go up or down?
Why don't we try to find a maximum?
Okay.
Right?
So then should we start low down?
Let's start low down somewhere.
Somewhere near here?
Okay, so should we start, what do you say we start right here?
Sounds good.
Okay. All right, so if we started there and we were using gradient descent, at least according to Giordano's method, we would say, okay, we're at that point. The first thing that I need to do is calculate the gradient there. Right? Once I've calculated the gradient, then I'm going to move from this point, right? So I'll call this point x1, right? To a new point x2, right? I'm going to say x2 is going to be x1 plus some constant, and I'm going to call it c. Giordano calls it lambda, which I don't like since that we already used lambda to talk about eigenvalues. But so plus some constant times the gradient of f evaluated at x1, right? Okay, so we want to calculate the gradient at this point. So what's the gradient look like there?
I guess it would be perpendicular to that.
So it's going to be perpendicular to this level curve, and it's going to be pointing this direction, right? Because that's going up, right? Because I'm going from the -6 contour to the -4 contour. So maybe the gradient looks something like that, right? So I'm going to move some distance, c times that gradient. So let's say I move this far to this point, right? That's c times that gradient. Okay, now at this point, I do the same thing, right? I come back up here, and I say, okay, I'm at a new point. I'm going to calculate my new gradient at this value. So where's the gradient there?
Probably pointing this way a
It
little
looks
bit.
it looks like, if I sort of look at these contours, it looks like it's maybe pointing in that direction a bit. So
That
I'll
sounds
follow
right.
that for a little while, right? Then I do the same thing again. I'm at this point. I look at that. Oh, it looks like the gradient is now pointing in this direction. So I follow that for a little while. Here, it sort of looks to me like the gradient is going to be pointing over there a bit. So I follow that a little while, and I keep on following it. Eventually, I get to this area. What's going to be true about the gradient there?
It should be 0. That's where we had our little
Right.
peak,
So one of the things that I expect to happen is that initially I'm going to be moving in pretty big steps, but once I get close to this, it's going to get little tiny. Why did I do that? So one of the things you'll note in Giordano is actually the way that he deals with that is he takes this constant c and actually makes this constant c a little bit bigger each time, so that the step size doesn't get too small as you approach this maximum. Now right away you can see kind of our problem here. What's the problem?
I don't know.
Well, one problem is that we've ended up here when the maximum
Is
here.
away.
Right? And this is a general issue with gradient descent, that you only can find local minima or maxima. Right? It doesn't guarantee that you find the maximum or the minimum. It guarantees you find a maximum or a minimum. And this is a weakness that you need to be aware of when you're dealing with gradient descent. But so this is how Giordano's approach works, right? And it's very much analogous to what you were doing on that Chicago problem from the last studio. Okay, let's talk about a different approach that I think has some interesting insight to it. It's very similar, but ends up having slightly different characteristics. One last thing before we talk about that. Notice that had we decided to start at a slightly different point, like say we had started here instead, we would have walked like this, then like that, then like that, and eventually we would have ended up at this maximum, right? Had we started maybe about here, we might have ended up at this maximum, right? So depending on where you start, you can end up at a very different maximum.
So I guess I'm wondering, is it just bad luck that in the first case we ended up at a local that wasn't the highest maximum?
Well, it was that you chose the wrong starting point, Rahana.
My fault.
Okay, I'm glad we're clear about that. Okay, so let's now think about, actually, let's stop there on this video and we'll make another video about the other method.